Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology. In this video, I'll be discussing some of the basic principles of climate change, just some general things on the science to help people understand it. So I'm actually filming this. I'm at Jockey Ridge State Park in North Carolina. It's just south of Kitty Hawk, where the Wright brothers had their first flight, and I'm standing atop one of the sand dunes, one of the natural sand dunes. I'll just swing around so you can get a panoramic view, and bear with me with the sound quality. It should be loud enough, but there is wind. It's quite windy here. So basically, we talk about the solar constant for the Earth, which is the watts per square centimeter. So watts is a power. It's the power of the electromagnetic radiation from the sun. Peaks in the visible region at about 700 nanometers, something like that. There's a distribution. You know, the sun acts as a black body radiator at 6,000 Kelvin, so it sends out a distribution of wavelengths that peak in the visible and then have a long tail. And when that radiation hits the Earth, the part that's absorbed heats up the Earth. The Earth then acts as a radiator at a temperature of about 15 degrees Celsius. You convert it to Kelvin at 273, so that's about 288 Kelvin. So the Earth is like a black body radiator at that temperature, roughly. It's a bit more complicated than that because it's the temperature of a region in the atmosphere. But and then that would send out a distribution of wavelengths that peak at about 10 micron in the infrared. And at that peak, we have the greenhouse gases, primarily CO2, nitrous oxide, and methane. Those are the ones that we've been increasing concentrations of. And of course, water vapor is a large one, which is really a feedback. So as we warm the temperature, we get more evaporation. For each degree of warming at the surface, there's about 7% more water vapor in the atmosphere. So the radiation on the outside of the Earth's atmosphere is about the solar constant. It's about 1360 watts per square meter. So for every square meter of area, 1360 watts, which is joules per second, energy per unit time. Okay, so the average at any particular part of the Earth will be 1/4 of the solar constant. Why 1/4? Because you're half of it is in the northern hemisphere, half of it is in the southern hemisphere, or if you like, I guess that's the case. And then also, we have 12 hours of night and 12 hours of day on average throughout the year. So that's another half of the time you're in dark, half you're in light, so divide by 2 again. So you divide the 1360 by 4 and you get 340 watts per square meter. So that's the energy on average at the top of the atmosphere in a particular region going and so where does that go? That has to go through the atmosphere before it reaches the ground. So as it's going through the atmosphere, some of the light is scattered by molecules, air molecules, mostly nitrogen and oxygen, and this is called Rayleigh scattering. And the scattering depends on 1/4 the wavelength to the 4th power. So if you have very short wavelengths like blue, then 1/4 wavelength to the 4th power is a very large number. So blue is scattered much more than red, where the wavelength is about, say, 700 nanometers versus blue 400 nanometers. So that is why red light transmits a lot further through the atmosphere. So when the sun is on the horizon, like it sunsets and sun rises, then most of the blue light will be scattered out long before you see it, and so you'll see the red light getting through. So it's why the sunsets and sunrises are red. The sky is blue, appears to be blue to us because blue is scattering a lot more than red as the infrared radiation comes through the atmosphere, so we see a blue sky. So you get scattering from the air molecules, which are very tiny. It's called Rayleigh scattering. You also get scattering, and so when the light is scattered, the electromagnetic radiation hits a scattering center, if you like, an air molecule, and then it goes off in all directions. There's also scattering from many other particles in the atmosphere. If there's small particles, if there's black carbon, for example, if there's ash from forest fires, if there's water, if there's droplets, non-water droplets are known as aerosols, so any chemical. So H2SO4, sulfuric acid from volcanoes, is up in the atmosphere. It dissociates into SO2, sulfur dioxide, and sulfur dioxide scatters light. So anything that scatters light in the atmosphere reduces the amount of light that reaches the Earth's surface. And then, of course, we have water vapor. And when the water vapor rises and condenses into droplets, we get scattering. So if there's very large droplets, there's less scattering than if the droplets are very fine and numerous. So one of the ways considered for solar radiation management to reduce the amount of light reaching the Arctic is basically marine cloud brightening. So if you have clouds composed of very large water droplets, then they'll scatter light, but they'll be like gray clouds or black clouds if they absorb lots. So if you make the droplets very, very small, very, very tiny, so if you start with like 80 or 90 nanometer droplets and have lots of them, okay, very high number densities of them, then they'll act as cloud condensation nuclei. So the water droplets, the water vapor that's rising will condense on these droplets, and because they're very, very tiny, they scatter a lot of light. So these clouds are very, very white looking clouds, and they reflect a lot of light, they scatter a lot of light. So that light doesn't hit the surface, so that would cause a cooling of the surface. So the idea of marine cloud brightening as a solar radiation management technique to cool the Arctic would be to take these low-level marine clouds about a kilometer and a half up, and make them whiter so they scatter light and they cool the surface below. So what else happens when that light, so the light can when light hits some material, it can either be transmitted, so it just passes through the material. It can be reflected. Think of a bathroom mirror, reflects about 98% of the light coming in because it's aluminum on a glass surface. And so the reflectivity or the albedo is very high. Or you can have absorption. So if you have dark materials like asphalt on the surface, that's got a very low reflectivity, or a very low albedo is another term for it. So in that case, most of the light is absorbed because it heats up the material. Think of walking on a dark pavement on a sunny day with bare feet, asphalt, very, very hot to the touch. If the surface is lighter, okay, it's not as dark, then that means it's going to be absorbing less sunlight. So that means it's reflecting more sunlight. Okay, so the sand I'm on right now, you know, white sand in a desert, it can reflect a lot of light. You know, maybe, I don't know, 80% of the light, 60 to 80%, depends on, you know, the whiter the sand, the more light is reflected, and that there's less light transmitted into the sand. Can't really go very far because sand's opaque. If it's water, the light can be transmitted deep through the water and absorbed in the water. And in fact, 93, 94, 95% of all the heating on the Earth is heating of the water from the solar radiation going in. So, but the light that's absorbed will cause heating of the earth. So the darker you know, as we take down a forest, which is, you know, very green, very dark, you know, it's got a high albedo, absorbs a lot of light, we replace it with a canola field or something, we change the albedo, which affects the heat balance at the surface. And that heat balance can affect things like how much air is heated, how much convection there is, and therefore how many clouds are formed, etc. So when we have a city that's filled with concrete and dark surfaces, the albedo is very low, it absorbs a lot of energy, so the city gets hotter and hotter. And so putting in a city, we get the urban heat island effect. There's a strong correlation, there's a nice curve between the logarithmic, if you take a log axis of the number of people in the city and take the urban heat island temperature rise as a result of that city being there, it's a pretty linear bit. We're talking about large cities having maybe 6 degrees Celsius warmer temperatures. Multiply that by 1.8, that would be about 11 degrees Fahrenheit warmer. This is why things like green roofs in cities, or using concrete roads instead of black asphalt roads, can make a big difference in keeping the city cooler, reducing the urban heat island effect. And of course that affects precipitation too, because if you have clouds carrying condensation in the clouds, so water droplets, as they reach a city, there's an urban heat island effect, so there's like a dome of heat over the city, and that can evaporate the water in the clouds. It can cause them to rain out, sort of like the mountain effect. All the rain is on the incoming side, and there's no water left in the clouds as you cross the mountain, so you get in the lee of the mountain, you get like desert region, you get rainforests in the side that the wind is coming from. Similar things to city. So, you know, if you had a farm, for example, and a city was put right in the path that the storms usually travel in front of you, then your precipitation can plummet. Okay, so all of these things happen. We study all of these things, and so, you know, we also have to think of the Earth as a sort of as a thermodynamic system. So, you know, the heat patterns are quite different on the Earth. Of course, the equators are much hotter than the poles, because the equators always get 12 hours of light, 12 hours of day. The sun is overhead more, so the path length of the sun's rays through to the equator is shorter. So there's less path length through the atmosphere. There's less scattering, so the light intensity will be greater. Also, the angle of the sun is much. The sun's closer to the zenith, whereas if you're at the pole, first of all, you know, there's periods where you get, you know, if you're north of the Arctic Circle, then you can get 24 hours of light in the summers and 24 hours of darkness in the winters. And but the angle of the light is much more glancing. So the area of the light impinging on the surface, because of the geometry of the Earth, is much larger. So that would be larger square meters of area. So the watts per square meter would be a lot smaller. So the solar intensity in terms of watts per square meter is a lot smaller, and therefore the poles are a lot colder. And so that temperature difference is key to determining what's happening in terms of, am I going the wrong way here? So that temperature difference is key in terms of determining the balance of heat on the planet. So I think I'll stop there so I don't fall over this sand cliff. And I appreciate you listening. Thank you. Okay, bye for now.